welcome again to to another lecture of solar photovoltaics principles, technologies and materials. So, what we discussed in the last class is last lecture is we will just review that. So, in the last lecture we looked at the evolution of solar PV technologies. There are three. So, the way it goes is first we have Gen 1 technologies, then we have Gen 2 and then we have Gen 3. Gen 1 is silicon primarily based on mono and multi crystalline. Then we have gallium arsenide. Gen 2 would be thin film and multi junction. Thin films would be CDT, CIGS, amorphous silicon and so on and so forth. Gen 3 will be with dye sensitized solar cells. So, this is called as emerging or new PV, organic, perovskite. There are other technologies also such as quantum dots, CZTS and so on and so forth, which fall under this category. Okay. So, now let us move to, so what we were doing in the last class, we were looking at the principles of cell design, and we said that optical depth should be high, the reflectivity should be low, there should be large built-in field for effective charge separation, junction should be closer to the surface, there should be small series and large shunt resistance, minority carriers lifetime should be larger, small surface recombination velocity should be lower, band gap should be optimum so that you have maximum efficiency. So, we are looking at, but most of the materials have band gaps between 1 to 1.7 eV, this is the range that you have. And then generally from the perspective of silicon, especially the emitter, which is the top layer, is heavily doped and base is lightly doped, and this helps in making better top contacts, because remember on top you have a limitation of having maximum. So, if you have a device like this, so this is silicon, right? Silicon is a opaque material, the light comes from top. So, you have to have very good contacts so that you can minimize the contact surface area on the surface, otherwise most of the light will get blocked. Okay. So, if you, because metal is opaque, right, the problem with the metals is that metals are opaque to light. So, when you are putting, suppose you put a whole layer of metal on top, then nothing is going to be absorbed. So, what you want to instead do is that you want to minimize this coverage, and as a result we put in contacts which are at various places, and such that you have efficient current collection, so that you do not cover the whole surface with metal, you have only very little coverage of the surface. So, that is why if you look at the top, you have these very thin lines running like this on silicon panels. These are grids basically, and they are arranged in such a manner so that you have minimum surface coverage, which allows maximum light penetration into the device. On the back, obviously, the back can be coated completely with metal, and this will give you very good collection in the base. So, that is why silicon has certain design issues, which we will see later on. And these two of course are contradictory. If you want, if you have large built-in field for effective charge separation, generally that results in smaller lifetimes and diffusion lengths, and these two generally go as contradictory. We will see later on in the course. So, you have to basically optimize various parameters. So, device design parameters, generally you should have a good quality junction. So, in case of silicon, it is N silicon and P silicon, so it is called as homo junction. In case of CIGS and CDS, for example, so CIGS is the P type material and this is the N type material. So, the junction is of two different material, that is why it is called as a heterojunction. So, homo junction is the junction between the similar materials, Heterojunction is the junction between the two different materials. So, in case of only silicon we have a homojunction, whereas in many other materials, in many other solar cell devices we have a heterojunction. Okay. And for a specific material, one needs to worry about what is the junction depth, what is the cell thickness, what is the doping level and the gradient of doping level, because doping level sometimes is not uniform. There has to be gradient in the doping level, especially from silicon perspective. There are some devices which require surface treatments to remove, for example, certain layers or to introduce surface. Then of course contacts, what kind of contacts you are going to choose. Remember, the contacts must be, in this case the contacts must be ohmic. So, you cannot choose every material. Okay. So, for example, if this is the silicon device diagram, this is the p-n junction you have. Now, you are saying that you want to have a reverse current. So, essentially when you are flooding the electron to, so you are saying you are moving the electrons from this side for the short circuit current. The electrons are going from this side to this side, right, and they get collected somewhere. Okay. So, the Fermi level of metal, so basically you are looking at the negative current, okay, you are not looking at the positive current, and here you will have holes which are created as a result of photoabsorption, and these are going to move here. Okay. So, you are going to look at these electrons in such a fashion, you are going to collect these electrons in such a manner, so that the Fermi level of electron the metal does not lie above. So, this is the metal contact. Okay. Metal contact. So, metal has a Fermi level, right. The Fermi level of the metal should be aligned in such a manner, so that you have electron collection. Electron should not be blocked by the energy level of metals. Similarly, on this side you have another metal. The Fermi level of metal should be such that the holes are not repelled, they are collected by the metal. So, metal must make a ohmic contact with respect to both electrons and holes on both sides of the solar cell, and that is why for a different material you will have different contact. You cannot use the same aluminum or same gold or same silver for every solar cell, it will vary depending upon the type of material. Okay. And that is why the choice of this material is extremely important. And then of course, we have this optical behavior of material. So, you do not have much control over it, but suppose if you are using silicon, silicon is a material with it has a poor absorbing capacity because it is an indirect band gap material, and it also tends to have recombination issues. Gallium arsenide on the other hand is a very good absorber, but it has high surface recombination. Okay. So, silicon has high bulk recombination and recombination at the rear as compared to gallium arsenide. Gallium arsenide is good absorber because it is a direct band gap material, but it has high surface recombination velocities. So, there are different issues with different materials which have to be overcome by adopting device fabrication strategies appropriately. So, let me now go to, we'll skip this part, we can I think go through this a little bit, the analysis of. So, if you do a simplified analysis of a PV device efficiency, let us say you have a power of 100 milliwatts per centimeter square, this is the input. Okay. So, if P in is equal to 100 milliwatts per centimeter square, this can be represented as Q into N photon into E average by Q. Okay. So, basically 100 milliwatts per centimeter square is nothing but product of number of photons into average photon energy. Okay. And I have put this Q in such a manner, so that I have average energy, number of photons and the electronic charge. This is essentially 1.6 into 10 - 19 coulomb multiplied by number of photons is 4.5 into 10^17 centimeter cube per second. This is the photon flux, and this is 1.382 volt. okay, the average energy. So, essentially this can now be equated as, this can now be equated with 72 milliamps per centimeter square into 1.382 volt, okay. And so, if I write eta, this is equal to JSC divided by 72 milliamps per centimeter square multiplied by VOC divided by 1.382 both in volts multiplied by fill factor, all right. Now, this can be further broken down into, I can write JSC as Q Eg to infinity NPH number of photons dE, basically photon flux, okay. And since all the photons are not, since not all the photons are capable of getting absorbed into the device, there are some which get reflected. So, as a result we can further break this down into this term Q. So, this, let us say this is A multiplied by Q into N absorbed divided by Q into Eg to infinity NPH into dE into JSC divided by Q N absorbed into VOC divided by 138. So, slowly and slowly you can see what we are doing. We are dividing this simple expression JSC VOC into fill factor into different quantum efficiency, the optical quantum efficiency, the absorption quantum efficiency, basically the how many get reflected here, how many get absorbed here, then finally we will break this down into, so this factor, the first factor comes to be about 0.257, okay, for let us say 2 electron volt semiconductor, okay. And if you talk of this factor, this will be approximately 19 milliamps per centimeter square for a 2 electron volt semiconductor. This factor, the one we see here, this depends upon the absorption, okay, how much absorption of material or how much reflection you have. So, essentially what you can do is that you can break this thing into smaller quantum efficiency terms to look at each of them microscopically. So, what basically we want to do here is, if you change the band gap, for example, you will increase this current, okay. If you reduce the band gap, you will increase this current. If you increase the absorption coefficient, you will increase the number of absorbed photons. If you decrease the reflection, then again you increase the number of absorbed photons. So, each of these terms, if you increase the, for example, if you change the band gap, you will change the VOC also, and this fill factor will depend upon the parasitic resistances that you will have in the device. So, this gives you a microscopic understanding of what you should do with the design at every stage to get higher efficiency. So, we will now move to our discussion on the technology part. So, we will first move to single crystal solar cells. We will primarily discuss silicon, and we will just look at the gallium arsenide device design without getting into details of that. So, these are Gen 1 technologies. So, let us begin our discussion with monocrystalline silicon solar cells. So, silicon has two various technologies. In the silicon BV, we have monocrystalline silicon solar cell, monocrystalline or single crystal solar cells, which means silicon is single crystal. There are no grain boundaries in the silicon. It has certain orientation. The wafer could be either 100 silicon or 111 silicon. So, which means if you look at the wafer, the top surface is 100 plane. Okay. If you look at this, the top surface is 111 plane. Okay. This can be distinguished by conducting X-ray diffraction. And the other case could be multicrystalline or polycrystalline silicon, where there are grains. So, this has no grains, this has grains. The grain size, however, is generally bigger than the device thickness. Okay. So, this is a condition which minimizes the loss of current or loss of performance of polycrystalline, otherwise there will be huge loss in terms of current. So, essentially you are looking at a configuration like this. See, if the grain size is smaller than the device thickness, you will have this kind of configuration, right. These are the grains. But so this is, let us say, grain size is D and thickness is T, this is D less than T. But if you have other scenario in which D is more than T, then this is your grain size, something like that. So, this is device thickness, this is grain size D. So, D is greater than T. So, when the carriers move up and down, they do not encounter too many grain boundaries. In this case, when the carriers will move here and there, they will find these grain boundaries which will trap the charges. Whereas, in this case, since there are fewer grain boundaries to encounter, there are only vertical grain boundaries, the charges do not face the grain boundaries, as a result they do not get trapped. So, this is a better design. That is why grain size is larger than the device thickness. In this case, the grain size is smaller than the device thickness. Then there is microcrystalline silicon, where grain size is smaller than the device thickness, which is what is this. In fact, D is much smaller than thickness. And then we have thin film silicon, where we generally use amorphous silicon. Thin film silicons are the device thicknesses of the order of a few microns, or of the order of a micron, whereas in this case the wave in all these three cases it is wafer thin. So, the whole thing is about 0.3 to 0.4 mm thick. So, if you look at the numbers, these could be updated a little bit better. So, monocrystalline, for example, has efficiency of about 24.7% laboratory scale. In the production, it has efficiency of about 14 to 18%. Polycrystalline has efficiency of 19.8% at the laboratory level, which is now about 21-22%, and production efficiency is about 15% as of today. Amorphous silicon, in fact, it may be a little higher than 15 as we speak today. Amorphous silicon laboratory efficiency is about 13%, in the production is about 8%. Monocrystalline silicon or polycrystalline silicon wafers have a thickness of about 300 micron, which is 0.3 mm, and amorphous silicon have a thickness of the order of a micron or so. Amorphous means there is no crystalline order. Basically, you have atoms having short atomic arrangement, having a short range order. So, what is silicon? In terms of material, silicon has a diamond cubic structure, which is basically a face centered cubic structure, and so 4 silicon atoms make up a FCC lattice, and remaining 4 atoms are tetrahedrally coordinated by other silicon atoms in such a manner, so that you have a diamond cubic structure. It is an indirect band gap semiconductor. As a result, it has poor absorption coefficient, and so essentially what it means is that you have, if you draw the EK diagram, so this is K, this is E. So, basically you can say this is your so these two do not, so this is conduction band minima, this is valence band maxima, these two, so the transition is like this. So, there is a transition in the energy space as well as in the K space. So, hence it has poor optical absorption, as we saw earlier. It has a band gap of 1.1 electron volt, and it has a refractive index of 3.4, natural reflectivity of about 40%. So, as a result, it is highly reflective. So, the effort is to minimize the reflectivity of silicon. and despite its poor absorption, can we make it work better? Silicon is generally doped by phosphorus and boron. Phosphorus to make it +5 and boron is +3. So, this makes it, this is for N type, this is for P type silicon. The VOC of the silicon thermodynamically cannot exceed 18.1% of the band gap. So, as a result, VOC maximum limit of the VOC is 0.88 volt. You cannot get more than that, and generally it is lower than that. Carrier lifetimes in silicon, in case of highly pure silicon, the carrier lifetime can be up to 10,000 microsecond or 10 millisecond, whereas in case of doped semiconductor, when you dope, you introduce scattering centers, as a result the lifetime reduces. So, if you as we saw last time that if you compare the absorption coefficient of silicon with respect to energy, the gallium arsenide goes something like that, silicon goes as a much smaller band gap. So, this is silicon, this is gallium arsenide. Silicon has lower absorption coefficient due to virtue of it being indirect band gap semiconductor. Silicon also has recombination issues, and recombination is generally radiative. It could be trap assisted and also it could be Auger. So, generally recombination rate is given as delta n by tau n for N type carriers, and this is basically the average of 1 over tau plus 1 over tau rad, 1 over tau Shockley-Reed-Hall and 1 over. So, this is radiative recombination, this is Shockley-Reed-Hall and this is Auger. This we saw earlier also, right. And lightly doped silicon, P silicon, generally Shockley-Reed-Hall dominates at our room temperature, and it has a lifetime of about 10 microsecond. And lightly doped N silicon has a lifetime of 1 microsecond, and again it has Shockley-Reed-Hall domination. So, this is why in silicon, since in N silicon the lifetime is lower as compared to P silicon, the N side of the solar cell is kept thinner and the P side of the solar cell is kept thicker. Okay. So, that is why N side is kept on the top and P side is kept at the bottom in silicon solar cells. So, that is why N is thinner, which we call as emitter, and we make P as thicker, which is called as base. However, if you heavily dope silicon, there is a tendency for Auger processes to dominate, and one needs to also optimize the surface recombination in comparison to the bulk recombination in silicon. So, recombination needs to be understood well to make a device with better performance. And if you look at the carrier transport in silicon, silicon has higher electron, so as a result of lifetime, the mobility of electrons in P silicon is higher as compared to holes in the N silicon for the same doping level. So, for example, electron mobility in P silicon is 1500 centimeter square volt second to roughly 70 centimeter square volt second. This is the range within which mobility varies, whereas in case of holes, it is 500 to 50. So, P silicon having higher mobility again is a reason why P side should be made thicker. So, as a result you have longer minority carrier diffusion length in P silicon, that is why P silicon is made thicker. So, this is the configuration generally we have. We have N type being made thinner and P type being made thicker, and then since the light comes from top, the top contacts have to be put in such a manner so that they do not cover the surface, they are sparsely located. So, this is the design criteria for silicon solar cell, that because of diffusion lengths and lifetimes and mobility and of course the diffusivities, again you can see the same trend goes in the diffusivities also. Diffusivity of electron is higher as compared to hole. So, this is for P silicon and this is for N silicon. So, that is why P type, which is the base, is far thicker as compared to emitter, which is the top, and you will put electrodes on top in such a manner so that these electrodes do not completely cover the surface, yet the electron collection is efficient. Okay. So, the basic design of a silicon solar cell will be a heavily doped very thin N type layer as top emitter and lightly doped thin thick P type layer at the bottom, which is base, and so it's going to look like something like this. This is P silicon, then we have N silicon on top, and the surface of this N silicon is little textured, and this is to improve the absorption. And then on top of that we have a layer of and the contacts are put somewhere like this. These are contacts put at various places. So, this is textured surface to maximize the light absorption, because you will have some internal reflection that will lead to, and then on top of this we have a anti-reflection coating. So, on top of this we will have anti-reflection layer. So, this is a typical device design, and on the back we will have electrode here. This is back metal, this top metal. So, we will look at the more details of silicon in the next lecture. So, what we have done in this lecture is just looked at the PV technologies from the perspective of silicon, what are the material design consideration, and so on and so forth. We will continue this in the next class with more discussion. Thank you.